It is the year 1666 and England is in crisis. The dreaded plague is spreading north from London. Universities close, and both students and teachers head home to safety. One such student travels north to his family's estate in Lincolnshire. One afternoon, while sitting and drinking tea, he observes an apple fall to the ground and begins to speculate about why all objects are drawn toward the center of the earth. Nearly 2 decades later, this same man publishes his theory of universal gravitation, which for the first time establishes the laws of gravity and simultaneously revolutionizes mathematics, physics, and astronomy. His name is Sir Isaac Newton, history's greatest scientist. The man known to history as Isaac Newton was born on Christmas Day, December 25, 1642, at the manor house of Woolsthorpe, south of the town of Grantham in Lincolnshire, in the East Midlands of England. At that time, England still used the Julian calendar. On the continent, where most countries had adopted the Gregorian calendar, the date was January 4th, 1643, 10 days ahead of the Julian calendar. Little Isaac was clearly sickly and underweight. It is understood that his mother believed he would die shortly after birth, which explains why he was not baptized until a week later, a ceremony that usually took place within 48 hours of birth. Whatever the circumstances, Isaac survived. He was named after his father. Isaac Newton Sr. was a landholder and an important farmer in rural Lincolnshire. The family's wealth was indicated by their residence at Woolsthorpe, a substantial manor house. The Newton family had built generational upward social mobility here from the early 16th century onwards and had become prominent members of the yeomanry by the mid-17th century, the equivalent of middle-class farmers. Isaac Sr. was uneducated and illiterate, a common condition among middle-class yeomen in the 17th century. Isaac Newton would never know his father. He died in early October 1642 at the age of 36, 2.5 months before his only son was born. Isaac Sr. left behind a sizable estate and a range of livestock, including 4 dozen cattle and 235 sheep. This wealth would influence Isaac's life and allow him to pursue a life of scholarship in later years. Isaac's mother was Hannah Newton, daughter of James Askew, a member of the gentry from the town of Market Overton in Rutlandshire. This reflects Isaac Newton Sr.'s upwardly mobile nature. Isaac Newton's mother, Hannah, remarried after the death of his father, marrying Reverend Barnabas Smith, a wealthy clergyman. She moved away to live with her new husband, leaving Isaac to be raised by his grandparents. Isaac's relationship with his grandparents was strained, and he grew distant from his stepfather as well. These difficult early family experiences are believed to have shaped Newton's reserved. Newton's life was also greatly influenced by intellectual, cultural, and social forces that had begun more than a century before his birth. The Renaissance is often viewed through an artistic lens, as a movement that produced great painters, sculptors, and architects. In reality, it transformed every sphere of European life in the 15th and 16th centuries, from philosophy and diplomacy to commerce and technology. One important offshoot of the Renaissance was the scientific revolution. Medieval European science was primitive. A certain amount of knowledge about astronomy, biology, mathematics, and the natural sciences had been preserved from the ancient Greeks and Romans. Yet, in many fields, European scientific knowledge was rudimentary during medieval times. This began to change in the early 16th century. First, a Polish astronomer named Nicholas Copernicus published a book entitled On the Revolutions of the Heavenly Spheres in 1543. In it, he laid out the heliocentric model of the universe, which stated that the Earth rotated around the Sun, and Copernicus's revelation that the Earth was not the center of the universe sparked a wave of scientific inquiry across Europe. Pioneers like Tycho Brahe, Johannes Kepler, and Galileo Galilei advanced fields such as astronomy, optics, mathematics, and physics, while developing new scientific instruments. The scientific method, proposing hypotheses and testing them through experimentation, emerged, building on ancient Greek philosophy and the concept of atoms. Though the scientific revolution reached England later, figures like Sir Walter Raleigh conducted experiments even during imprisonment. English navigators improved cartography in pursuit of new trade routes. In the 17th century, England became a key center of scientific progress, with leaders like Sir Francis Bacon, William Harvey, and Robert Boyle, the latter recognized as the father of modern chemistry. The founding of the Royal Society in 1660 brought greater collaboration among natural philosophers. Isaac Newton's early years are not well documented, as he rarely wrote about his childhood. After his stepfather died when Isaac was 10, his mother returned to Woolsthorpe with his younger half-siblings. Isaac's education began under the guidance of his cousin Richard Askew and later at a grammar school in Grantham, where he studied Latin and was introduced to mathematics. At 16, Isaac briefly returned home to work on the family farm, but disliked it. Recognizing his intellect, his teachers helped finance his continued education, leading him to attend Cambridge University in 1661. Due to his modest background, Newton was a sub-Caesar at Cambridge, performing chores and excluded from dining with wealthier students. This social isolation pushed him to focus deeply on his studies, guided by tutors like Benjamin Pullen. Aristotle, a key figure in medieval scholasticism, was both a philosopher and an early natural scientist. Newton initially studied Aristotle but shifted focus after 2.5 years at Cambridge to modern scientific, philosophical and political works, especially those of Galileo. Inspired by Galileo, Newton began original research in mathematics, physics and optics. As Newton's education ended, England faced a series of events that set the stage for his groundbreaking work. In late 1664, a large comet appeared, seen as a bad omen. Early in 1665, a severe outbreak of the bubonic plague struck England, including university towns like Cambridge. With no cure, people fled cities to avoid infection, creating conditions that would influence Newton's life and work. During the plague outbreak of 1665, many wealthy people fled cities like London, Bristol, Cambridge and Oxford to their country estates. Newton retreated to his family home at Woolsthorpe when Cambridge University closed. This period of isolation, known as his annus mirabilis or miracle year, allowed him to make groundbreaking advances in physics, mathematics, and optics. Newton built on his earlier work from Cambridge, developing the binomial theorem and foundational concepts for modern calculus. Although he wrote a significant paper on motion, he did not publish it immediately. He then focused on mechanics, aiming to expand upon the work of Galileo and René Descartes. René Descartes, a philosopher who, 30 years earlier, had coined the famous phrase cogito ergo sum, I think, therefore I am, as a basis for an objective, unquestionable truth that could form the foundation of a philosophical system. Building on the work of Descartes and using his own advanced mathematical skills, Newton began developing a new theory of how gravity functions. By studying the collision of objects, he discovered that objects exert forces on one another when they meet or clash, causing them to move in different directions. However, he observed evidence of a center of gravity along a straight line. Through further experimentation, Newton concluded that particles or atoms attract each other, and that the force involved in this gravitational pull depends on the masses of the objects and the distance between them. This complex concept was linked to several other conclusions he reached in his notebooks during 1665 and 1666 regarding force, gravity, and mechanics. One of the simplest laws of physics he formulated at this time is his third law, which states that every action has an equal and opposite reaction. For example, when you jump into the air, gravity immediately pulls you back down by the same distance. While some of Newton's mathematical and gravitational laws were complex, taken as a whole, they represented a fundamental expansion of human understanding about gravity and motion. A fanciful story later emerged that Newton formulated his theory of gravity after watching an apple fall from a tree at Woolsthorpe. This tale was likely inspired by the story of the ancient Greek mathematician Archimedes, who famously made a great discovery about buoyancy while taking a bath. In the long run, Newton's mid-1660s discoveries about gravity, weights, and mechanics were his most important contributions. However, beyond mathematics and physics, Newton also made significant discoveries in optics, the study of light, color, and vision. His experiments reveal how Newton approached his research. To test whether rays emitted by different colors were perceived differently, he painted one end of a piece of thread red and the other blue, then observed them through a prism. As he expected, the colors appeared distinct, demonstrating what is now known as Newton discovered that light can appear more intense and available depending on different conditions. He then expanded his research by setting up a dark room, allowing only a narrow beam of light inside. He placed a prism in front of the beam and refracted it onto a wall over 20 feet away. The resulting color spectrum was 5 times longer than it was wide. From this, Newton realized that light was not homogeneous, but heterogeneous. It was not made of a single substance, but consisted of different parts, visible as the various colors in a light prism. Newton called this the corpuscular theory of light, describing the components of light as corpuscles. This research later formed the foundational basis for Albert Einstein's discovery of photons nearly 2.5 centuries later. By the end of 1666, Newton had made several breakthroughs in mathematics, physics, and optics. However, no one yet knew the extent of his accomplishments. He carefully recorded his remarkable findings in notebooks at Woolsthorpe, but had not shared them publicly. It was not until the spring of 1667 that it was considered safe to return to Cambridge. Life in southern
England had been severely disrupted by the final stages of the plague and the Great Fire of London in September 1666, which left around 100,000 people homeless, many encamped outside the ruins or dispersed to towns and villages across the country. Amid this atmosphere of disorder, Newton returned to Cambridge and was elected a fellow, a position providing a modest salary. He began teaching, tutoring, and continuing his research, while starting to share some of his findings in a limited way. For example, he summarized some of his mathematical work in a tract titled On Analysis by Infinite Series, which he distributed to several colleagues. Though this was hardly a grand example of academic self-promotion, and it is debatable whether his peers fully understood the complex equations he presented, it was enough for the university to recognize Newton as a mathematician of exceptional skill who had made significant breakthroughs during the plague year. Consequently, in 1669, he was appointed Lucasian Professor of Mathematics, a prestigious chair that had been founded only a few years earlier. The Lucasian Professorship was established in 1663 through a bequest made by Henry Lucas shortly before his death. Lucas was a parliamentarian who had represented Cambridge during the English Civil Wars of the 1640s. Newton held the Lucasian Professorship for 33 years, though his final years were mostly absentee as he moved to London in the mid-1690s. The position was hardly demanding. Newton was expected to deliver 1 lecture per week during 1 term of the year, for which he received an annual income of $100. Moreover, the lectures attracted very little audience, reflecting the low interest in mathematics and physics at Cambridge in the late 17th century. By 1687, Newton was excused even from this light teaching load and had no further teaching responsibilities. These lectures, however, allowed Newton time and space to refine his mid-1660s findings and make them more accessible. To demonstrate his discoveries to the few students who attended, he developed instruments such as telescopes and prism rings to showcase his theories on optics. Gradually, Newton's findings began to reach a wider audience. By 1671, the Royal Society in London had heard of his work and invited him to submit information about his research. Newton was elected a Fellow of the Society in January 1672. His membership enabled his findings to spread beyond Cambridge to the broader academic community in England and then to the continent, as many Royal Society members corresponded extensively with natural philosophers and scholars abroad. In an era before academic peer-reviewed journals, this correspondence was the primary means of disseminating new research. Despite this, Newton refrained from publishing much of his work. His paper On Analysis by Infinite Series was distributed among colleagues and eventually published in 1711, along with a few other works. However, Newton waited over 20 years after his breakthroughs at Woolsthorpe before publishing them fully. As Newton emerged in the 1660s and 1670s as a leading scholar, he showed no interest in marriage or starting a family. In the 17th century, it was expected that a man of his social status would marry, have children, and seek to advance socially. Newton neither pursued this nor seemed to consider it, showing little interest in the opposite sex. This has understandably led to much speculation. There is no evidence to suggest that Newton was gay. Rather, he appears to have been largely asexual, showing no interest in sexual relationships. Historians were surprised years ago to learn of a possible teenage fling Newton had with the stepdaughter of Mr. Clarke, with whom he lodged while attending grammar school in Grantham in the mid-1650s. This was unusual given his typical disinterest. The conclusion is that Newton was heterosexual, but had very little interest in women. Over time, he abandoned any thoughts of marriage or family, if he ever seriously considered them. Instead, he devoted himself fully to his research and writing. Newton was reclusive and did not socialize much at Cambridge. When he visited London in August 1674, he made no effort to meet with Royal Society members he had corresponded with for years. Instead, he returned to Cambridge a week later and continued writing to them about his work. As he aged, he became slightly more sociable. His religious views were unorthodox. Although Protestant, like the majority of English people in the late 17th century, Newton was a nonconformist who disagreed with the established Anglican Church. His nonconformity was extreme. He rejected the doctrine of the Trinity, the sanctity of God, Jesus, and the Holy Spirit. However, he kept these beliefs largely private, which have only been reconstructed through analysis of his notebooks. Newton's aloof and often difficult personality sometimes led to rivalries and conflicts with fellow scientists. These disputes were sometimes simple academic disagreements, such as with Christian Huygens, a leading Dutch mathematician, philosopher, and astronomer. While Newton was still a child, Huygens discovered Titan, Saturn's largest moon, in 1655. Huygens was already a renowned scholar across Europe when Newton was unknown. Both men developed competing theories on the nature of light. Huygens rejected Newton's corpuscular theory, proposing instead that light traveled in waves that generated secondary waves, or wavelets. A significant academic debate unfolded between them over many years. A more toxic rivalry developed between Newton and Robert Hooke. Hooke, 7 years older, was also a natural philosopher, mathematician, and astronomer. He dabbled in surveying and engineering and oversaw much of the rebuilding of London after the Great Fire of 1666. In the 1660s and 1670s, Hooke worked on telescopes, optics, and gravity, and saw Newton's rise as a threat to his own eminence within England's scholarly community. This unpleasant rivalry lasted for decades and is famously believed to have ended, with Newton ordering the destruction of all portraits of Hooke held by the Royal Society after Hooke's death in 1703. Despite such rivalries, Newton shared common interests with many other English natural philosophers, including alchemy, esoteric thought, and what was known in early modern Europe as Hermeticism. Newton's interest in these areas was lifelong. Alchemy involved the quest for the fabled philosopher's stone, a legendary substance believed to transform anything into gold. It was closely linked with beliefs in magic and hidden or arcane knowledge. Hermeticism was a branch of alchemical studies, named after the teachings attributed to a mysterious figure from late antiquity called Hermes Trismegistus. He was thought to be a philosopher and proto-scientist dabbling in alchemy. In reality, the works ascribed to Hermes were largely derived from a mix of Neoplatonic philosophy by 3rd century AD writers such as Plotinus, and science practiced in the Roman Empire during the 3rd and 4th centuries AD. Elements of ancient Egyptian law and other writings were also incorporated into Hermetic and alchemical thought in early modern Europe. Thus, Hermeticism functioned as a kind of pseudo-religion, involving experimentation with arcane knowledge. Hermeticism was closely connected to the scientific revolution. Newton and Leibniz were not alone among major scientists dabbling in alchemy and Hermeticism. Figures like Nicholas Copernicus, Tycho Brahe, Johannes Kepler, Galileo, Walter Raleigh, Francis Bacon, Robert Boyle, and many others were involved as well. The scientific revolution was deeply linked to the quest for the philosopher's stone, alchemical studies in general, and Hermetic thought. Chemistry, in particular, emerged directly from alchemical studies. A visitor to Newton's study over many years would have seen scientific instruments designed to test substances for their suitability as the philosopher's stone, while his papers were filled with manuscripts on alchemy and Hermeticism. As early as the 1660s, Newton's growing interest in chemistry led him to conduct alchemical research. He obtained a 6-volume work entitled Theatrum Chemicum, published in 1602, which contained extensive treatises on performing alchemical experiments. Newton studied this and other works closely, even as he conducted groundbreaking work in physics and mathematics. By 1670, his alchemical studies had advanced enough that he composed a treatise of his own titled The Vegetation of Metals. Vegetation meaning transformation in this context. Around this time, Newton considered abandoning natural philosophy and physics altogether to focus on alchemy. He corresponded with Robert Boyle, the leading chemist of the age, and continued developing his laboratory at Cambridge. There he carried out new experiments, acquiring various substances and equipment to study them. This work resulted in the creation of an Index Chemicalis, or chemical index, in which he recorded experiments with hundreds of substances in search of the philosopher's stone. Newton eventually compiled thousands of pages of notes on alchemy, much of which was written in symbols he clearly understood, but which are now indecipherable to modern readers. This adds to the impression that he engaged in arcane research. In fact, he probably devoted more time to alchemy than to physics. Newton's interest in alchemy and Hermeticism extended into what today we would call esoteric history and thought. Esoteric means mysterious or hidden. An example is Newton's fascination with the myth of Atlantis, described in Plato's dialogues, Timaeus and Critias. Newton incorporated discussion of the legendary utopia into a lengthy book titled The Chronology of Ancient Kingdoms Amended. This work explored the chronology of ancient civilizations such as Egypt, Greece, Babylon, Assyria, Persia, and others from antiquity. It must be remembered that when Newton wrote about these societies, the disciplines of Egyptology, Orientalism, and archaeology had yet to emerge, and the history of ancient Egypt and Mesopotamia was still shrouded in mystery. Some of Newton's work was historically based, while other parts blended history and myth. This also fed into his interest in the Old Testament and obscure elements of Christian theology. For example, Newton was fascinated by the Book of Daniel, an apocalyptic text in the Old Testament that discusses the end of days. Worryingly, his research into apocalyptic texts led Newton to calculate that the world could end in either 2034 or 2060, suggesting we might not have long left. His interest in the more obscure historicity of the Old Testament also saw him writing extensively about the Temple of Solomon, the first temple in Jerusalem, and whether it had indeed been built by King Solomon. Newton concluded that these ancient buildings and their associated religions were evidence of long-lost knowledge systems, of which alchemical studies formed just one aspect. In the end, Newton did not abandon his work as a natural philosopher to become a full-time alchemist, a transition that, in modern terms, would have been switching from physics to chemistry. Instead, he continued to focus on natural philosophy while moonlighting in alchemy. We are fortunate he did because, in the 1680s, he began condensing his research into one of the most important books in the history of science, Philosophiæ, Naturalis, Principia, Mathematica, the mathematical principles of natural philosophy. Completed in 1686 and published in 1687, it synthesized all the work Newton had undertaken since his student days at Cambridge. While he had shared much of this through papers and correspondence since the mid-1660s, Principia provided a refined account of his findings in gravitational laws, mechanics, and mathematics, greatly advancing European scientific knowledge. For example, while Galileo and Kepler had observed and described planetary motions nearly a century earlier, Newton was now able to provide a scientific and mathematical explanation for why planets moved as they did. His work also expanded understanding of equinoxes and ocean tides. Newton even theorized about how gravity, physical phenomena, such as observations of irregular motions in the moon, were also explained in Newton's work. His Principia Mathematica would soon come to be regarded as the most important book written during the scientific revolution. The Principia is divided into 3 books. The first, entitled De Motu Corporum, on the motion of bodies, provides a detailed description of his theories on gravity and the laws of motion, including his discoveries about gravitational pull, force, and equal reactions that he had made at Woolsthorpe back in 1666. This book also discusses the work of earlier scientists like Johannes Kepler and explains how bodies move due to forces like centripetal force. These theories are expanded upon in the second book, where Newton directly responds to arguments made by René Descartes and others on the continent in previous decades, systematically showing where their analyses were flawed. Finally, the third book, subtitled De Mundi Systemate, on the system of the world, attempts to demonstrate the real-world implications of the theories described in the first 2 books. For example, much of the discussion in Book 3 focuses on how the laws of gravity and force impact the planets and the solar system. Newton also outlines his views on the nature of the solar system and the heliocentric universe. In this way, the Principia Mathematica not only presents new theories, but also discusses the vast body of material that constitutes the scientific revolution, reaching back to Copernicus's discoveries about the solar system and the Earth revolving around the Sun a century and a half earlier. One aspect that slightly dims Newton's accomplishments is that many of the same conclusions were independently reached at the same time hundreds of kilometers away in Germany by Gottfried Wilhelm Leibniz. Born in 1646 in the city of Leipzig in Saxony, eastern Germany, a few years after Newton, Leibniz attended numerous universities in the 1660s and embarked on a career of exceptional scholarship. Like Newton, Leibniz was a polymath who cannot be easily categorized as a mathematician, physicist, or philosopher. He worked in a wide range of fields, and as Newton increasingly did throughout his life, he also worked for governments and performed various administrative and bureaucratic roles, including working for Peter the Great, Tsar of Russia. Leibniz worked to modernize the Russian state in the early 18th century. His research led him to make many of the same discoveries Newton was making in England between the 1660s and 1690s. In particular, both men independently developed calculus, though Leibniz's approach was more practical. He even invented the Leibniz wheel, a basic mechanical calculator. Their discoveries were so similar that later in life, a heated, academic dispute arose, with both claiming to be the first to make these breakthroughs. During this conflict, Newton disingenuously used letters exchanged with Leibniz in the 1670s to accuse him of copying his findings. What this reveals is that societies must reach a certain level of knowledge in a field before individuals can make specific breakthroughs. Both men arrived at the same conclusions simultaneously because they built on the work of Galileo, Kepler, and others. Similar cases occurred in other eras. Over 150 years later, Charles Darwin and Alfred Russel Wallace independently developed nearly identical theories of evolution and natural selection. Meanwhile, Newton published the Principia Mathematica just as England entered a period of significant political instability. 2 years earlier, in 1685, King Charles II had died. Though he fathered many illegitimate children by multiple mistresses, his marriage to Queen Catherine of Braganza was childless. Without a legitimate heir, the throne passed to his brother, James, Duke of York. The problem was that James II was a Roman Catholic during a time of strong anti-Catholic sentiment in England and Scotland. Political tensions worsened when James's son was born in the summer of 1688 and was raised Catholic, raising the prospect of England returning to Catholicism. James did little to ease fears and began placing Catholics in powerful positions in England and Ireland. Within weeks, a coalition of English aristocrats and politicians wrote to James's son-in-law, William of Orange, the most powerful figure in the Dutch Republic and husband of. Life in London exposed Newton to a wider intellectual and social environment. He took on additional responsibilities, including serving as warden and later Master of the Royal Mint. These roles gave him influence over England's monetary policy and allowed him to apply his analytical skills in practical affairs, such as combating counterfeiting. Newton's later years were marked by a shift away from pure scientific research toward administration and